Good evening, and welcome to Beckman Auditorium and the Watson Lectures at Caltech. I hope the party out front was good, and that you had a chance to talk to some students and maybe peer through some telescopes that were provided by the Astro Outreach team. Yes, do I see some nods? Okay, good. At least a few of you got that experience. I'm Crystal Dilworth. I'm a Caltech alum, neuroscientist, science communicator, and your host this evening. And I'm so glad that you all wanted to come and join us in this community of curiosity and Caltech's 102nd season of communicating science to the public. And I especially want to call out any high school students in the audience. Yes, high school students. Clap for yourselves. Caltech's Junior Watson program allows students from local high schools to come on campus, tour labs, talk to scientists, and hear about opportunities to study science and technology at our Center for Teaching, Learning, and Outreach. And we've been doing this for many, many seasons, and we're so glad that they also want to come to the show. So thank you for being here. The Watson Lectures have always been free and open to the public, and since Beckman Auditorium opened its doors in 1964, been had right here on this stage. And as the auditorium's patron and namesake, famed inventor Arnold Beckman is known to have said that it is fun, friendship, sympathetic understanding, and many other aspects of warm human relationships that contribute so much to our joy of living. And so tonight, we get to sit under this beautiful ceiling that sparkles like the night sky and have a few of the secrets of life in the universe illuminated by the research of Professor Katerina Chatziioannou. But before we learn about her research, we're going to hear a little bit about her as a person. There'll be an introduction from the Executive Officer of Astronomy, a short video that will tell you a little bit more about her story, and then, after her lecture, you guys will have a chance to ask your questions. So a QR code will appear on the screen that will allow you to submit your questions using your phone. If you're not comfortable doing it digitally, flag down one of the ushers. They will have comment cards. You can write your question there, and they'll make sure that your question gets uploaded so that I can get to as many of the questions in the audience as I possibly can. All right, I think that's the business. So it is time for you to turn off your cell phones and your watches and all of the tech that you brought with you that makes noise. Note your nearest exits, and please help me welcome to the stage Caltech's Executive Officer of Astronomy, Andrew Howard.
Good evening, everyone. It is my great pleasure to introduce Katerina Chatziioannou. Katerina works in one of the most exciting areas in all of science, the study of black holes, neutron stars, and other objects that warp space-time. This is a field that, as many of you know, was started more than 100 years ago by Albert Einstein. It began in a completely mathematical basis, but experimental tests soon proved the validity of this theory and put it on a firm foundation. The field is also one that has inspired multitudes of people, young and old, including myself as a teenager and probably many of you in this room today. The pace of discovery in this field has accelerated in the past few years, especially with the results of LIGO. LIGO is an experiment that Katerina is going to tell you all about. And amazingly, it has discovered dozens of new black holes in the universe, literally by taking a new way of looking at the universe. So our speaker tonight, Katerina, grew up in Greece. She attended the University of Athens. Her PhD is from Montana State University, and she has postdoctoral fellowships at the Canadian Institute for Theoretical Physics and also the Flatiron Institute. Katerina joined the Caltech faculty in 2020 as an assistant professor of physics, and she now also holds the title of the William H. Hurt Scholar at Caltech. She's the winner of many awards, including the Alfred P. Sloan Fellowship, the Department of Energy Early Career Award, the Jürgen Ehlers Thesis Prize for the top PhD in general relativity and gravitation. So in 2020, when Katerina arrived here at Caltech, we, the other faculty and the students, were not here. It was the pandemic, of course, and everyone has their own pandemic story and will remember where they were and what happened. For Katerina, that meant that she met all of us on Zoom. She met her and recruited her research group on Zoom. In fact, Katerina told me that she wrote her first set of papers with students here at Caltech whom she had never met in person, only on Zoom. So since then, since the pandemic has abated, Katerina has had a dynamic presence on campus. Her field straddles two fields, physics and astronomy. And so Katerina maintains two offices in those two departments, and she zips back and forth across California Avenue as we try to understand the physics of black holes and the astrophysics of the explosions that they create. So we at Caltech are delighted to have her here as part of our community, and I'm sure that you're going to be delighted to hear her talk. We're first going to have a video, and then we'll welcome to the stage Katerina.
I grew up in Greece, and then I moved to the US for a PhD. I was a fifth-year grad student when the LIGO made its first detection of gravitational waves. It was obviously something very exciting, and everyone immediately dropped everything and started working on that. The first detection of gravitational waves came from black holes. A few years later, we had neutron stars, so basically my career has been going where the data is. When we have data about black holes, I work a lot on black holes. When we have data about neutron stars, I work on neutron stars. I'm Katerina Chatziioannou. I'm an assistant professor of physics and William H. Hurt Scholar, and I work on general relativity and gravitational wave astrophysics. Black holes are almost simple, even though the gravity in them is so extreme. They're almost simple objects because it's just gravity, nothing else. A neutron star is the most dense material object that exists in the universe. If you want to go beyond pure general relativity, this is the only object that allows you to do that. And the properties and forms in which matter can find itself when it's put in such extreme conditions, how it behaves, what it looks like, and that is infinitely more complicated to understand. We see neutron stars with gravitational waves when they're colliding with each other, and we use that signal to try to understand what happened, what the collision looked like, what the neutron stars looked like. It's a hard problem to solve because it involves objects and conditions that we have no way of replicating. You just receive what you're lucky enough to get from the universe. The ultimate goal is to learn as much as we can about the properties of neutron stars and black holes, but the process is, something that you have to enjoy in order to get to the goal. If you only like finding the answer, you only like 1% of your work. I would say most of the time you go slowly to the solution. Sometimes physics moves ahead and math needs to catch up by creating new concepts. Or math goes ahead and mathematicians study something that looks abstract and doesn't have any real-life application. And then years later, physicists find out that it actually does explain some unknown phenomena that they hadn't understood before. Why does math explain the world? If you think about it, it's not as obvious as it might sound.
Good evening.
Tonight, I will tell you a story about what happens when matter and gravity clash and how we can observe that with gravitational waves. Gravity is the most fascinating of all the forces that shape the world around us. We all have an intuitive understanding of what gravity is. We know that if we drop something, it will fall. At the same time, people have been observing the night skies for centuries, and we're actually able to understand and describe the motion of the planets around the sun to remarkable accuracy. The unification of these two ideas by Newton in the 17th century was a milestone for modern scientific thinking. Newton described both of those phenomena through the same fundamental principle of gravitational attraction, namely, if two objects have a mass, they will attract each other. Today, of course, we know that this is not the whole story for gravity. Gravity should instead be described with general relativity, which is, in my opinion, the most beautiful of all the theories of gravity, or theories of physics that we have. General relativity instead says that gravity is not something, a force that acts on top of our world, but it is a fundamental principle of our world itself in the form of the curvature of space-time. Now, general relativity is a daunting theory. It's very complicated. The math is complex. The concepts are very complicated. I think of it a bit like moving to a new country without speaking the language. You have to simultaneously figure out how to communicate in a new language, while at the same time be aware of which kind of idioms or phrases from your old language might not translate to the new language. However, general relativity has a major advantage. It has a messenger. Gravity is no longer something that is passively waiting for us to understand. Instead, it can talk to us with gravitational waves. Gravitational waves are gravity's messenger. This is a numerical simulation of two objects, let's call them black holes, going around each other. And this motion of the black holes around each other creates gravitational waves that propagate away from the system. Those are the colorful ripples that move away from the system and then travel through space at the speed of light, carrying vast amounts of energy. And when I say vast, I mean truly vast amounts of energy. If you could concentrate the energy carried by a wave like this and appropriately convert it, you would be able to blow up the entire sun. Hopefully, we cannot do that. We can't concentrate it, so no one needs to worry. However, as this energy travels away from the system, it is removed from the system, which means that the two black holes will get closer and closer together, and eventually they will collide. The simulation is getting to the late stages, and I think it is worth taking a second to admire the late stages. It will slow down, and there you go. The two black holes, very close to each other. You see how they start wobbling. And now they join into one, and you have a final burst of radiation, a burst of waves that moves away from the source. Quite spectacular. Now, if you're having a hard time wrapping your brain around what gravitational waves are, don't worry, you're not alone. It actually took physicists decades to even convince themselves that they are real. Famously, Einstein himself did not believe they were real. He tried to publish papers showing that they don't exist. He was wrong. It happens to the best of us. But deep down, the way I like thinking about gravitational waves is that in terms of waves, and in a physics textbook, a wave is defined as a moving disturbance that carries energy. And we kind of visualize this disturbance to understand what it is. So to understand what they are, think of something like a cylinder of particles. Each of the dots here is a particle, and it's placed in a kind of cylinder configuration. And then a wave travels in the direction of the red arrow. So this is what will happen to the particles as the wave travels through. You see that the particles move, but they're not really going anywhere. They just move about the same position while this disturbance moves forward. Essentially, what happens as gravitational waves travel through our universe, they change the distance between objects. But that's not exactly the distance in physical space, that's the distance in space-time. Remember, this is general relativity. We have to relearn our entire vocabulary. Now, there are numerous ways today to detect gravitational waves. Most of the detections, and indeed the first direct detection of gravitational waves, was achieved by the LIGO detectors, shown here on the left, LIGO Hanford, and on the right, LIGO Livingston. And the LIGO detectors are essentially these 4-kilometer long vacuum tubes whose size we can measure to about 10 to the minus 18 meters. Now, I could spend all day discussing what an absolute ridiculous statement it is to measure something to 10 to the minus 18 meters. This is the outcome of decades of hard work by hundreds of physicists and engineers, a lot of whom are here at Caltech, as Caltech, jointly with MIT, hosts a LIGO laboratory that constructed and currently operates the detectors. So on any day, if you walk around campus, you will almost certainly run into LIGO scientists who can, better than me, explain how you can measure something to this astonishing precision. Now, gravitational waves were famously first detected directly in 2015 by the LIGO detectors. And I'm going to show you here the signal in a second. So let's take a second first to see what's going to happen. On the top, you will see the data as recorded by the LIGO Hanford detector, and the bottom will be the LIGO Livingston detector. The y-axis is the frequency, so you see the units here, and the frequency is something like 100 hertz or so. This is the audible band. This is what our ears can hear, which allows me to play the signal for you, and the x-axis is going to be time. So there we go. That whoop at the end is when the black holes actually collide. There's another quite famous gravitational wave detection that happened in 2017. And this is quite unique because we didn't just observe this in gravitational waves, but it was also observed with light, electromagnetic radiation, across almost the entire spectrum. Optical light, which is what our eyes can see, radio, X-ray, etc., with major contributions from Caltech astronomers and Caltech telescopes. So here, I'm going to show you the data in LIGO Hanford, LIGO Livingston, and our partner Virgo in Europe. This is a longer signal, so I'm going to start playing it halfway through. You don't immediately see it, maybe, but it's going to become visible in a second. Focus on Livingston. Once you see it, you can't miss it. Yeah, now it's pretty clear. Yeah, this is why we play the sounds. They're quite cute. Tip, try playing them for your pet. They are amused. Okay, but we're not here to only talk about the highlights. I also want to talk about the science, because a lot has happened since 2015, and now we have detected dozens of signals with gravitational waves and LIGO. Okay, so we have all those signals, and in astronomy, when you get signals like this, they do not come with a label. They don't tell you what caused them. They don't tell you where they're coming from. So in astronomy, when you receive something like this, a sort of detective game begins, which is basically, okay, what is this? What happened? What did we just observe? So let's take a step back. Let's go back to theory to understand what we could have observed. General relativity tells us that in order to create gravitational waves, you need a lot of matter, and I mean a lot of matter, or energy, and you need to accelerate it. Now, the first condition is not that big of a problem. There are a lot of very massive things out there. There are objects that have millions or billions of times the mass of our sun. The second condition is the problem, the acceleration, because you have to take those objects and accelerate them up to basically the speed of light. This is why those kind of systems that I showed you in the simulation a few slides ago work very well. We call them binary systems. And it is the motion of the black holes around each other that gives you this acceleration, this large acceleration that you need in order to create gravitational waves. You can think of it if you're in a car and you're driving around a corner, you feel the centrifugal force pushing you to the out of the corner. That's the kind of acceleration that you need to make gravitational waves. At the same time, you need a lot of acceleration. You know that if you want to go to a racetrack and go around a high-speed corner at 200 miles an hour, you need a good car to do this. You can't take a Model T for this, you need a good race car, right? So same thing happens here. We need a very good, sturdy objects that are well put together in order to be able to sustain the kind of accelerations required in order to make gravitational waves. So it's not just that we need a lot of matter, but we also need a lot of matter compactified in a small region of space such that those objects are sturdy and can sustain those kind of motions. So let's look at what kind of objects would work. So we have to think about matter out there and how to pack matter tightly. So let's start, for reference, with water. Water packs matter about 1 gram of matter per centimeter cubed, almost by definition. Solids are obviously more dense. The center of the Earth has a density 10 times higher than water, while the center of the sun is about 100 times more dense than water. Okay, these are not bad, but still nothing spectacular. Why not? Why can't we do better? So matter itself, at the fundamental level, is made out of atoms. And the cores of atoms, their nuclei, are very dense. For example, the core of hydrogen, its nucleus, essentially a single proton, has an astonishing density of 14 orders of magnitude higher than water. So why is matter around us not more dense? The reason is that atoms themselves are not just made out of their nucleus, and away from the nucleus is mostly empty where the electrons are. So there is hope. If we start packing atoms more tightly, maybe we get higher densities. The name of the game is compact objects. That's what we're looking for. And out there in the universe, there are a lot of type of objects that we can go and see if they would work. As it turns out, the vast majority of them does not work. So the schematic here just shows you a collection of possible objects. Most of them will not work, but there's a few that might. So let's only talk about the ones that do work. One option are objects called white dwarfs. They have a density 6 orders of magnitude higher than water, and they pack the mass of the sun in about the size of the Earth. Quite good, right? Quite impressive. However, those would still not work for LIGO. On the other kind of extreme, we have black holes. Black holes are made when you compress matter so much that it just collapses into a space-time singularity, and at their center, the singularity, the density is formally infinite. How much compression you need? You need to take the mass of the sun and compress it down to about 6 kilometers or 4 miles. For reference, this is what a black hole would look over Pasadena. This is the kind of compression I'm talking about. Very small region. This object has the mass of the sun. Okay, but black holes are almost kind of cheating. There is no matter. Matter has basically collapsed into a singularity. As it turns out, there is one object that still works, because it's very dense, but still has some matter. This is what neutron stars are. They have a density of 15 orders of magnitude higher than water, and you get a neutron star when you compress the mass of the sun down to about 25 kilometers or 14 miles. And of course, this is a neutron star over Pasadena. Now, neutron stars are truly astonishing objects. The matter inside of them looks nothing like the matter that we're used to around us. Their name does not mean that they're only made of neutrons, but their name comes from the fact that neutrons are the most critical of the particles that make them up. Now, what happens? Gravity pushes you down. The gravitational attraction of the neutron star pushes it down. So in order to avoid collapsing into a black hole and disappearing forever behind the horizon of the black hole, you need something to support you against that. You need some kind of outward pressure to support against the crushing force of gravity. And it's the neutrons that provide that pressure. That's why they're called neutron stars, because neutrons are critical. That is a weird kind of pressure. It's nothing like we're kind of used to around us. It's called degeneracy pressure and has some quite weird properties. Now, neutron stars are really astonishing because they are some kind of weird balance between matter and gravity. Matter and gravity have managed to find this balance right before you collapse to a black hole to make those objects. The matter is essential. If you didn't have the matter, if you didn't have the pressure from the neutrons pushing you out, it would just collapse into a black hole and disappear forever. However, the gravity is also essential because this is what glues the neutron stars together. This is not true for most objects around us, right? So my body is not held together because my heart attracts my liver with gravity. However, this is what happens with neutron stars. If you turned off the gravity in neutron stars, they would just explode. They wouldn't stay there because the pressure, the outward pressure from the neutrons would just cause them to explode. Okay, so these are the objects that work. Black holes and neutron stars are the objects that work that LIGO could detect. So let's go back to our detections. The schematic here shows you again all our detections with LIGO. The way to understand this is, remember, you have a binary system of two objects. So each of these little kind of systems has two objects. Those are the objects in the binary that merged together and emitted gravitational waves and gave you a third object. So each of these collections of three dots linked by an arrow is a gravitational wave signal. And because this is gravity, the best thing we can measure is the mass of those objects. And so we plot those on the y-axis is the mass of the objects that we observed with gravitational waves. So now starts our detective game. What are those? Are those black holes or are they neutron stars? As it turns out, we have a major help, again, from theory that tells us that it's absolutely impossible to have a neutron star above this line. This is a fundamental limitation of nature, telling you that nothing can travel faster at the speed of light, and this is why you can't have neutron stars above this line, which is about 3 times the mass of the sun. This is great because it solves our problem from the majority of our signals. Everything that's blue here is definitely a black hole. And once you know these are black holes, then you can start answering a lot of very interesting science questions about them. Some of my personally favorite ones is what are the spins of the black holes, how we can use them to test general relativity, how we can measure their properties robustly. A number of Caltech graduate students and postdocs are working on these and other questions, and I would never be able to do justice to all their discoveries in just 30 minutes. However, I did want to thank them for all the interesting science. Instead, what I want to talk about is the neutron star for the story of today. Okay, so this requirement, this kind of 3 solar mass threshold, solves our problem immediately for most of the signals, but there's some left. So what I'm talking about today is all the little dots below this orange horizontal line. Now, immediately you see there aren't that many of them, right? There's way fewer. These are more rare. We don't detect them as often, which means that every single one of them is a treasure trove. We really need to do our best to understand every single one of them. Okay, so what happens there? We have objects that have a mass of about 1-2 times the mass of the sun, and they could be either black holes or neutron stars. So let's look at the options. Let's understand the options better. This is to scale, just to give you an idea of the size of a neutron star on the left and a black hole on the right. And let's place those objects in kind of out in the vacuum of space. A black hole itself is characterized by an event horizon, which is the surface beyond which nothing, not even light, not even another black hole, can escape. But the event horizon is not really a physical surface like a wall. You can cross the event horizon just fine, and you go basically from vacuum to vacuum. The inside of a black hole is also vacuum. Neutron stars, on the other hand, have an actual physical surface. If you follow them, you're going to hit a wall. And the inside is made of matter. It might be more different matter than anything we're used to, but they are made of matter. At the cores of black holes, we think we have space-time singularities. The question mark is intended to denote that we think. Well, at the cores of neutron stars, we have matter. However, matter has found itself in such complicated configurations that we don't really know what that matter actually looks like. This is the million-dollar question. What matter is actually doing inside neutron stars? How has it managed to twist itself in such ways to provide so much pressure to avoid collapsing into a black hole and disappearing forever behind the event horizon of a black hole? For us, studying those objects, this kind of big million-dollar question is related to 2 other questions that we want to understand. One is, how big are neutron stars? Literally, what are their size? Options range between 16 kilometers to 32 kilometers. And how massive can neutron stars be? We know they can never, ever be above 3 times the mass of the sun. But how massive are they actually? 2, maybe 2.5 the times of the sun? Those are the exciting questions for us. Now, there's one more final fun fact about neutron stars. It's personally my favorite of the fun facts that actually makes our lives a little bit easier. Now, the world around us is incredibly diverse. This chair, for example, has a mass, 20 pounds. If you take then a 20-pound dumbbell, it doesn't look at all like a chair. A 20-pound chair and a 20-pound dumbbell look nothing like each other. The world around us is diverse. That's not what happens for neutron stars. Neutron stars are clones of each other. If you take one neutron star that has a mass 1 times the mass of the sun, and another neutron star that has a mass 1 times the mass of the sun, they're identical. They're basically the same object. They're clones of each other, which really makes our life much easier. So when I say how big are neutron stars, I don't mean how big is that neutron star we discovered over there versus that neutron star we discovered over there. I mean all of them. How big are they? Okay, so then going back to our scale for those objects, a black hole will have a radius of about 6 kilometers. A neutron star would have a size of about 8 to 16 kilometers. Now, this is kind of bad news because those two numbers are not that different from each other, 8 and 6 or 16 and 6. For us observing them from a very large distance, those objects are kind of similar to each other, right? They're not that different. But it turns out they're not identical. There is one critical difference that we can use. So to understand that difference, let's go back and take some inspiration from the map of the Earth. This time it's not Pasadena, it's actually Greece, where I grew up. Athens would be here. And this island here is called Evia, that's where I grew up. And that island, if you squint here, is barely an island because it goes really close to the mainland. Actually, that canal is about 50 feet wide, and in there, water flows. This is a video of the quite strong current flowing north to south under a drawbridge. But it doesn't flow like that constantly. It flows like that for 6 hours, and then 6 hours later, it reverses and goes south to north. And then 6 hours later, it reverses again and goes north to south. Does that sound familiar? Those are tides. These are tides that we learn in school caused by the moon going around the Earth, causing the oceans to move around. Tides basically are caused by the fact that the moon is big, it exerts a lot of gravity, and the Earth is not a point object. It has a size, it's big. It has a front face facing the moon and a away face going in the other direction. Does that sound familiar? A lot of gravity and big objects that are not point particles? This is a numerical simulation of 2 neutron stars merging. Neutron stars are quite good, sturdy objects. Gravity really glues them together, so they maintain their composure for a long time, but not forever. Eventually, gravity will win and tear them apart. And that's where they merge. If I just freeze the simulation right before they merge, you see the shape they have. They're no longer the nice, perfect little spheres. Compare that to the shape of the Earth as the moon goes around it. The physics is the same. This is tidal interactions between the 2 neutron stars, same way you have tidal interactions between the moon and the Earth. The math is, I can't describe how different it is. General relativity is very complicated. It is difficult to explain the effect, but the physics principle at work is the same. Those are tidal interactions. And we can use that, and let's use it for this signal. This is actually one of the popular ones, the famous ones, the one that was also observed with light, with electromagnetic radiation. And to be fair, because it was observed with electromagnetic radiation, we actually have a pretty good idea that those were neutron stars and not black holes. However, now we can not just confirm that those are neutron stars that merged and gave that signal, but also measure their sizes by measuring tides. To get an idea of how this works, there's a lot going on here. Don't worry about this. All all I want to show here is that those colored lines is what the gravitational wave signal from those two objects looks like if they were black holes, or if they were small neutron stars, or if they were bigger neutron stars. So the signal is very different, and we can go about measuring that. So the big idea is, the big thing we want to measure is how big are neutron stars. This was done in a research project led by Caltech graduate student Isaac Legret, who over a series of papers solved out the technical and conceptual details of using that data to place constraints on the size of neutron stars. And by the way, the first in this series of papers is one of those studies that Andrew referred to at the beginning when I first got here during the pandemic. So that view of Isaac is sort of how I had met him at the time, through a Zoom window. So that's what I thought he looked like when we published our first paper. Okay, so let's see what we found. Using again a map of Pasadena centered at us to understand what we have. So before we have any information about neutron stars, we think their sizes could be 8 kilometers or 16 kilometers in radius. For reference, a black hole would be here. Okay, this is getting crowded. Let's remove all that. And then let's delve into Isaac's work. Isaac used data about neutron stars to decrease that uncertainty to get a better idea of how big neutron stars are. So if you include radio data about neutron stars that all existed before our work, you get something like that. If you include X-ray data, you get something like that. And next step is where gravitational waves come in. There you go. This is what the gravitational wave data do to you. You have a size for neutron stars of about 12.5 kilometers, which is sort of in the middle of where we started, between 8 and 16, right? Great, so we had a pretty good idea of what the uncertainty was before we started. It's about 12.5. Still, we have uncertainty of about 1 kilometer, so we can't directly answer the question, what is exactly inside neutron stars? But we know how to solve this problem, and we need more data in order to get better and better measurements. I do want to take a second to appreciate what has happened here. Those objects that gave the signal we observed on that day in 2017 were millions of light years away. And through the gravitational wave signal that we detected, we were able to say 16 kilometers, nah, that's too big. They weren't 16 kilometers big. 15, still too big. Maybe 14 or maybe 13. You can measure the size of those objects that are millions of light years away, thanks to gravity. This is what happens when you have extreme matter clashing with extreme gravity. Okay, so going back to our signals, we've talked about this one, and then there's a few more left. This is where things are becoming a little bit more uncertain, because these are the signals for which we still don't have a very good idea of whether they're black holes or neutron stars. So far, I've been talking about two possibilities. Either you have two black holes colliding to give you a gravitational wave, or you have two neutron stars colliding to give you a gravitational wave. Actually, there is one more possibility, which is a black hole and a neutron star. And I really can't resist showing you another simulation, because it's truly gorgeous. This is a neutron star going around a black hole. The black hole is a small one. The neutron star is a big one. They're going around. They're emitting gravitational waves, getting closer and closer together. And now watch what happens. The neutron star just fell in, right? It's kind of odd. The neutron star was bigger to begin with, but it was the one that was swallowed by the black hole. You can't really beat a black hole, right? You can't, even though it's smaller. Okay, so the objects then we're talking about, remember, are the ones below the orange line, the ones with masses 1 to 2 times the mass of the sun. So why can't we tell whether they're neutron stars or black holes? As it turns out, the reason we can't tell is because in this kind of shaded region, there's a bit of an ambiguity. We don't know what is going on here. We know that neutron stars can never, ever be more than 3 times the mass of the sun. But we don't know whether they can be up to 2 times, or maybe up to 2.5 times the mass of the sun, or maybe 2.6. So this shaded region is our ambiguity region. What happens here is that essentially matter is fighting really hard against collapse. It's literally fighting for its life against disappearing behind the event horizon. And in order to increase the mass even a little bit, pressure, the outward pressure supporting against collapse will have to go up by something like an order of magnitude. So matter is fighting really hard. It's trying its best. And the ultimate question is, how long can matter keep fighting for before it disappears into a singularity? We don't know the answer to this question. So with this context, let's go back to our detective game of what are those objects. So here we're looking at the masses of those objects. Remember, we have a binary system, which means two objects. So in the plot here, I'm going to start showing you the mass of the more massive of the two objects on the horizontal axis and the mass of the least massive of the two objects on the vertical axis. The orange lines are kind of our thresholds, right? We know at 3 solar masses we have a threshold, so anything to the right of that line is definitely a black hole, but we still have those ambiguity regions where we actually don't know what is going on. Those are the shaded regions. So what are the rules of the game, then? If something falls in here, it's 2 neutron stars. Easy. If something falls in here, it's a black hole and a neutron star. Great, we're making great progress. If something falls in here, okay, now things start becoming difficult. This could be a black hole plus something that we don't know what the other object is. If something falls in the yellow regions, it is a neutron star plus something else that now we don't know what it could be. Or if it falls in here, yeah, or if it falls in here, all bets are off. These are the rules of a game. And I do want to emphasize, the game of looking at where our detections fall in this plane is literally what we do. When we get a detection, we get the masses, we measure the masses. So when our codes, when our analysis find those signals, and I get an automated email that tells me, hey, we found a signal, here are the masses, I do this kind of quick game in my head and say, oh, okay, where does it fall? Is it a neutron star? Is it a black hole? Is it ambiguous? Do I have to pay more attention? Okay, so let's play the game for the signals that we have. The first one that I talked about, the popular one, falls in here. This is 2 neutron stars. Okay, great, we solved the problem. You notice that those are not kind of dots because we still have some uncertainty on how we measure the masses, so there's going to be some extent in how massive we think those objects are. Okay, let's look at the next one. What do you think? Mostly falls in the neutron star plus neutron star region, but extends in the ambiguity region of the yellow part, so probably 2 neutron stars. But, you know, always some uncertainty. How about this one? Mostly black hole plus neutron star, this part, but it still does extend the ambiguity region. So not always keep your options open. How about this one? Okay, not bad. Mostly black hole plus neutron star, again, extends a bit the ambiguity region. How about now? Yeah, I don't know. This doesn't just go in the ambiguity region. This actually crosses the threshold, right? So it could either be a black hole plus a neutron star or 2 neutron stars. And now you're not ready for what comes now. How about that? Yeah, I don't know. The honest answer is, I don't know. Nobody knows. OK, so what do we need to do to solve this problem? We think we know how to solve this problem. The issue is that we have all these large regions of ambiguity between 2 and 3 times the mass of the sun. We need to reduce them. We need to understand better what happens there. So this is work done by Caltech graduate student Jacob Gollum and Isaac that you met earlier. And our idea for how to solve the problem is a kind of a classic nature versus nurture approach. So what happens is neutron stars could exist between 2 and 3 times the mass of the sun. This is the ambiguity region here. Let's remove that. And we know that there's an absolute limit. Neutron stars can never, ever be above this line. So maybe in reality, what happens is they are up to this line Maybe this is what matter can do. This is the nature part. This is the physics written at the cores of neutron stars tell them that they can be up to this mass. But at the same time, it's not just what's written at the cores of neutron stars that matter for what LIGO detects, but it's also what the environment around them does. This is the nurture part. Let me give you an example for what this means. In order to get signals for LIGO, you have one neutron star and another neutron star, and they collide. If our sun collapsed into a neutron star tomorrow, it won't, don't need to worry. But if it did, would it be able to give a LIGO signal? It would never be able to do that because it doesn't have another neutron star around it. So it's not just whether those neutron stars are out there, but also can the environment around them allows them to create the kind of strong gravitational wave signals you need for LIGO. Jacob is an expert in measuring the blue part. Isaac is an expert in measuring the yellow part. So they joined forces to measure both and compare them and get an uncertainty that looks kind of like this. So far, nature seems to win, but we have large uncertainties and we still need more data. If we decrease those uncertainties, we will be able to, for example, compare this object with the limits that we measure and say whether it is a neutron star or a black hole. Currently, we can't because we still have large uncertainties. But I keep saying we need more data, and that's where the future is headed. There are a lot of very interesting questions to address with gravitational waves. Today, I discussed only one of them, which is, in my opinion, one of the most exciting puzzles, which is what happens at the terminal fight between matter and gravity, and when does matter give up. However, a lot more interesting questions we can address with more data. So this schematic kind of gives you an idea of what I mean by more data. So the way to understand it is the following. Think of us, the Earth, as sitting at the center of this circle. And then as you observe out in the universe, you go out in this circle. Most neutron stars and black holes are nowhere near us. They're not in the solar system. They're really far away. So these are the yellow dots for neutron stars and white dots for black holes that are really far away in the universe. Most of them are really, really far away. And the arcs, the colors, are like this, are estimates for how far out our detectors can observe those signals. So obviously, the more sensitive the detectors, the further out they can observe, so the better for us. As the detectors get better and better, they will observe more signals. This colored line, I know it's gray, blue, light blue, gray line, is results up to 2020. So these are the results I talked about today. Currently, the detectors are better. They're observing a signal about every 2 days, and we have about 200 more detections in the can that we're analyzing, and we hope to be able to talk to you about them soon. Around 2027, we have projected sensitivity of the detectors, something like the dark blue line, while we also have ideas for next generation detectors, the pink here and the green, that will be able to observe all binary black hole mergers in the universe. Let's take a second to understand what this means. This field in 10 years has gone from making the first detection to, in a few decades, being able to observe all signals everywhere to the edge of the universe. So if you're a young scientist looking for a data-rich field to apply your talents to, maybe you don't need to look any further. Or if not, and you're just interested, thanks for joining for the ride, and I'll be happy to answer questions.
All right, it's your turn. Use the QR code, submit your questions, and we'll get right to it. When I am at home for Thanksgiving with my mother watching my sister's in the audience, I can hear her laughing. We will be watching every single military-themed detective television show that has ever been on TV. But the emotional payoff at the end of finding the culprit is that justice can be served. What is the emotional payoff for being able to actually classify what it is you're looking for? Like, what does it tell us, and where do we go from there?
Yeah, so if you want to answer kind of science questions about those objects, you need to fundamentally know what they are. One of the big themes that I didn't address here, for example, is we want to test general relativity. We still don't understand everything about the theory. We still don't know what happens inside black holes, all those questions. So in order to do this, we need to know what we're looking for. For example, if we have a signal, a gravitational wave signal, that is caused by neutron stars, but we actually think is caused by black holes, and we try to test general relativity with it, we'll get the wrong answer because we don't fully understand what is going on. This is basically being able to understand what you observe is sort of the starting point. You can't do anything until you've answered that question first.
So we're still checking if our understanding of physics is the correct one?
In terms of understanding whether general relativity is the correct description of gravity, this is a big, long story. And yes, there's still some things that we're not 100% sure about, and the reasons to keep testing. So yeah, this is one of the big things we need to do with LIGO.
For LIGO, sort of what is the next step for LIGO itself? I mean, you talked about the next generation detectors, but for the LIGO project, what is next?
Yeah, improvements. It will keep getting better and better. So we already have planned improvements to take us to 2017, where we see hundreds more signals. And ideas even beyond that. The next generation detectors I talked about are going to be brand new facilities because actually the basic structure of the experiment changes. We go from 4-kilometer long arms, those tubes we had, to 40 kilometers. So someone is going to dig a 40-kilometer long trench. So thankfully not me. No, I mean that would be a lot of work. More like 2. Yeah.
Can you dig in a little bit more as to why we can hear the LIGO data? Like, why is it a sound?
It's a sound because we convert it to sound. So in order to kind of understand what gravitational waves are, the first thing we need to convey is that they're not the same thing as light. They're completely different things. So a good analogy is you understand the world around you with what your eyes can see and what your ears can hear. So if light and the electromagnetic radiation we've been detecting so far is what our eyes can see, then a good analogy is the gravitational waves are what we hear. Now, where the analogy becomes even better is because LIGO can detect signals with a frequency of about 100 hertz, say 10 to 1,000, which is centered at 100. Which is exactly what our ears can hear. So you can literally take the output channel of LIGO, convert it into noise and hear it. And I'm not kidding. People have done this, and people have used this kind of conversion to even do science. There's a famous example where there was some kind of unknown noise in LIGO until somebody played the sound, and it was a phone ringing, so somebody had forgotten the phone somewhere. Yeah.
Talking about noise in your data.
Yeah.
Okay, if we could see neutron stars with our bare eyes, could we see them, and what do you think they would look like?
We could see them if they were very close, yes. And we could see them also with telescopes, just standard telescopes that observe light. Some of the results I talked about don't rely on gravitational waves, but also rely on other observations of neutron stars that are made with light. They would look like a dot. They are pretty good spheres, so they would look like a dot. You don't want them to be much closer than that to look bigger than a dot, trust me.
I have a question here about 3-body collisions. Ooh. What would that look like, and have you seen any?
We have not seen any, which is not to say that we're not searching and we're thinking that something like this could happen. That goes back to the question of nature versus nurture, which is, black holes and neutron stars exist out there, but in what kind of configurations does the environment around them put them into? And there are ideas that they could be put in configurations of 3 objects that are close to each other. So it is possible for 2 of them to collide, and the third is just kind of, lurking around. And the signal that we detect will be affected by the third object, and we are searching for signals like this.
So it would be a big win.
It would be amazing, yeah.
Okay, I have to ask this question because it has so many upvotes, but the person that submitted it couldn't even put their name on it. So Anonymous is asking, how does gravity agree with quantum mechanics?
It does not.
There, you have your answer.
It does not, and this is one of the kind of fundamental big questions of modern physics, how to unify the two. It is interesting. It's an interesting problem because it's something that we think should be happening conceptually. You know, we really think it should be happening because they describe the world in fundamentally different ways. So they can't both be true, right? The problem is that as far as the black holes I talked about are concerned, general relativity, and without any quantum mechanics, describes them quite well. And as far as we can tell, there is absolutely no indication that general relativity breaks. So the problem is we know that it must happen at some point, but from what we've seen so far, we haven't seen this, and even worse, we didn't expect to see anything. The black holes that merge here would not have any imprint from quantum mechanics. Famously, what we think the impact of corrections, when you combine quantum mechanics and general relativity, where we think that those effects would appear are at something called the Planck scale, which is, hold on to your chair, 10 to the minus 35 meters. Yeah, it's hard. The black holes I talked about are 6 kilometers in size, which is, I don't know, 30 whatever orders of magnitude off. So it's hard when you think that something should break down at some point, but you have no experimental way to actually see it happening. So you're kind of, moving blindly, trying to come up with a new theory without the experiment helping you.
It's one of the things that has always struck me about astro. I mean, being a neuroscientist myself, is just the scales, that you have to deal with are so massive. And the way that we have interacted with the data has changed a lot, right? From looking through telescopes now to computation. Tell me how artificial intelligence is helping us understand what we're detecting and the data that we're getting and going to be getting in the future.
Yeah, so machine learning and AI are typically indispensable when you're talking about a lot of data and you're trying to find patterns in your data. We're not in that regime. We're nowhere near what we'd call the big data regime. I talked about 100 detections, right? And we're actually also extremely lucky that our data are not that big in size. We have quite, this is not like particle physics where you have to delete data because you literally cannot store it. We don't have that much data. But still, there are a lot of things that we need to do better at. This kind of approaches will work better than what we currently do in situations where you don't fully understand your problem. In situations like this, where it's a black hole or a neutron star, you kind of understand what the options are, and you can directly work through those two options. If you are not sure what the options are, if you have too many signals, you have millions of those signals, which is where the future is headed. Or you have so much data that you're not able to sit down and write down, these are the options, a black hole or it's a neutron star, or you have way too many options. This is where you need those kind of techniques.
So keeping on the topic of scale, if we don't know how big the universe is, how will we know if we've measured all of the binary black holes?
Yeah. So when I say we're going to measure all the binary black holes, that means that we'll go so far out in the universe that we'll get to a stage where we think that black holes of this form no longer exist. So this is not 100%, there is some disagreement on this, and actively people are working on it. But most of those black holes that we are seeing come from stars like our sun, way more massive than our sun, but stars like our sun that went through this whole evolution and eventually collapsed to black holes. For our sun, that takes billions of years. It won't collapse, it won't die for another 4 billion years. So that takes a lot of time, which means that those black holes take a long time to form. So it doesn't matter, how big your universe is. If you go so far back in time that you think it's impossible, there is enough time for them to form by that point. You think that this is sort of where they're starting forming in the age of our universe. Because it takes a long time to do that. Thankfully, our universe is not young. It's quite old, so it has already had the chance to make those black holes for us to detect them. That's why if you go really far back in time, we don't think they exist anymore.
There is an eventual limit that you will hit. But there's a theoretical prediction of a white hole by Carlo Rovelli. Mm-hmm. Do you think there will be the opportunity to detect these using LIGO?
Almost certainly not. If a white hole existed, we would have already detected it. Their sort of defining property is that stuff comes out of it, and so much stuff would come out of it that we would have seen it.
Another question. You said all neutron stars are the same. Mm-hmm. Don't neutron stars have rotation as well that could make them different?
Yeah. You can go into those details, like there's some small differences like this that could differentiate between them. At the level that we're talking here, that they are either 12 kilometers or 13 kilometers, those kind of effects are negligible. But if we get to the stage where we can measure how big they are to 12 kilometers versus 12 kilometers plus 50 meters, we have to start worried about little things like this. But again, thankfully, the basic idea carries over, that yes, if they spin, they will look slightly different than if they don't spin. But again, two neutron stars that spin with the same spin, they will look the same.
So taking us a little bit back to LIGO specifically, do the LIGO detectors need to be on at all times? Is there a maintenance period? What are the practicalities of that quite complicated experiment?
Yeah, it is extremely complicated indeed. And me, as someone who is taking the data and analyzing it, I would love if they were on all the time. The experimentalists would probably collapse of exhaustion if that happened, so they cannot be on all the time. So they do have times where they take them down either to do major improvements, which means they take them down for years, and then they come back online again, or they take them down once a week for smaller maintenance around the sites, or they just completely fall out of this good configuration they need to have in order to detect signals. They're extremely sensitive, which means that anything that happens around can unfortunately disturb them. So if an earthquake happens, they will knocked out of operation. Or if storms happen, knock them out of operation. So ideally, we'd like to have them locked and observing for as long as possible. But practically, this is, they cannot constantly be observing, and people need a break as well.
Is there such a thing as stronger or weaker gravitational waves that the detectors can't or aren't sensitive enough to detect? Or
yeah, absolutely.
What are the limits of LIGO?
Absolutely. So if this is a gravity experiment, so the main thing that matters is the mass. So if something is more massive, the signal is going to be stronger, and we'll be able to detect it more easily, which means we'll be able to detect it further out in the universe at a larger distance. If something is smaller, we need to detect it we can only detect it if it's close by. So the current limits of LIGO is it can, as you go to high mass, it can detect things better and better, up to about black holes that are maybe 200 times the mass of the sun, 300 times the mass of the sun. Beyond this point, its sensitivity starts dropping off. And as you go to lower masses, the problem starts being that those signals are weak, and something around maybe a little bit below 1 times the mass of the sun is where things are becoming very uncertain. They have those objects who have to be very close by for us to see them. But honestly, for me, this is sort of my hope for the future, to see one of these very low mass signals. It's just that they have to be very close, and we have to get lucky.
Why is that so exciting for you? Why is this the area that you've chosen to put time into investigating?
You mean the gravitational waves and neutron stars? Why it's exciting to me? I think fundamentally, what I find exciting is general relativity and the concepts of general relativity. This idea of translating between an old language, which is Newtonian gravity, to a new language, which is general relativity, and especially thinking about concepts that carry over from your old theory, like the tides I talked about. You have them between the moon and the sun, and you have them, sorry, between the moon and the earth, not the sun. Or you have them between two neutron stars, so the physics is kind of the same, but you have to explain in completely different terms. So thinking what changes, what is different, what is the same. I find this a very interesting puzzle.
Well, thank you so much for sharing your work with us. I'm gonna ask one more question, and that is, if you were to, as I'm sure you do as a professor, pitch this area of research to a potential student who is thinking about going into science, why should they choose this type of science, this type of research?
I thought you were going to ask me to pronounce my last name.
No.
No, this is what everyone asks.
That's too hard.
No, not for me. I can do it. Honestly, I don't think I can pitch this to anyone. People should work on whatever they find exciting. I found this exciting, so I can, if there's a student who's thinking about it, I can describe what I like, and I can describe what the day-to-day is. But at the end of the day, you know, it's your decision. What do you find interesting? I can't convince anyone it's interesting if it's not interesting for you.
Well, I hope there's a few out there that were convinced tonight. Everyone, please help me thank Professor Chatziioannou.